Hello and welcome, guys, for the last class on periodic classification and periodic properties. We had discussed in greater details on sizes, atomic and ionic sizes, and ionization enthalpies, first, second, third, fourth, electron affinity versus electron gain enthalpy, electronegativity, how to determine in different scales, including the Allred-Rocco scale. And also, we discussed last time the oxidation states, the maximum oxidation states and maximum oxidation state and minimum oxidation state for every group of elements, and those which exhibit variable oxidation state can go up to. Can anyone tell me in the D block the maximum oxidation state goes to the highest value in which group? And what is that value?
Sir, group 7.
And what is the highest value?
Sir, +7.
And what are the elements? At least tell me the three elements present in group 7.
Sir, manganese, technetium, sir, rhenium.
Fantastic. Can you tell, Bisma, you try to tell one compound or one ion in which manganese shows an oxidation state of +7. Bisma, that is the highest. Tell me one compound or one ion in which manganese shows the oxidation state of
K. So KMnO4.
KMnO4 precisely, or MnO4 minus, where it is +7. But there is another question. What is the highest oxidation state in the D block? And which elements they show? Isma, Swayam? Group wise, yes, you are correct. Yes, Bisma?
Yes, sir, +8.
+8, Karo, whose?
Sir, osmium.
How?
Ruthenium.
Osmium most stable. Yes. +8 is the highest state, although it goes up to +7 highest, then decreases, but exceptionally, ruthenium and osmium shows +8 state. Particularly, osmium tetroxide is very, very stable. Good. Another question in the P block. Can you tell me why in the carbon family lead 4 oxide is a very unstable and it is a strong oxidant? And also lead 4 chloride, what we say plumbic chloride, is not existent, doesn't exist at room temperature. Why? Swamjit?
Sir, bond energy. Sir, because bond energy
No,
decreases.
don't try to explain. First tell me one word or two words. It is due to this. Then, if you are asked, can you explain that? Then you will explain. What is the reason?
Sir, unstable ହେଇଥାଏ sir,
No, Bisma.
Sir, loss to stability more stable figure
Oh
than
my
+2.
God. Oh my, why? What is the main central reason behind it? Tell me in 2 words or 3 words.
Sir, ଆଉ ଥରେ କହିବି?
Huh?
Sir, ଆଉ ଥରେ କହିପାରିବି?
Yes.
Sir, relativistic effect.
Huh? What? No. Well, that is not meant for +2 level. But before that, I told you another effect. You are missing out that. I give you another chance to tell me why PbCl4 doesn't exist, why BiCl5 doesn't exist at room temperature, why the higher oxidation state becomes unstable as you go down the group, and the lower, less than 2, oxidation state becomes more stable. Why? What is that effect called? You can look to your copies and tell me.
सर सर कोई भी
Uh,
सर इनॉट पेयर इफेक्ट
yes, that is called the Innott pair effect. If there is one mark question to answer why PbCl4 doesn't exist at 25 room temperature, why BiCl5 doesn't exist at room temperature, why thallium trichloride doesn't exist at room temperature, all these due to Innott pair effect. If I ask you what is Innott pair effect, then you will say as you go down the group, the NS electron pair becomes more and more Innott, and so reluctance to participate in bonding. Then I will say why? Again, why? Because the bond energy that is formed after bonding cannot adequately compensate for the excitation energy from the NS to vacant NP level. But the actual cause that has been found is the relativistic contraction effect, which we cannot at this stage we cannot write. But I have sounded you that the 6s electron, particularly in lead, bismuth, thallium, the outermost electron is present in 6s, and that because of the relativistic contraction effect, they become so tightly bound. You know, their the contraction due to because they move with high speed, and therefore they have heavy mass. Relativistic mass becomes more, and they have more penetration, more than expected. As a result, the ionization enthalpy is little more. Thallium is the second highest, and it doesn't like the 6s electron to lose. Therefore, only p electrons take part to give you TlCl, thallium monochloride, not TlCl3, PbCl2, lead 2 chloride, without any participation of 6s, which becomes tightly bound, reluctant to unpair and go to the vacant p orbital and form bonding. So with this, we will not spend any more time. Yes, I remember the doubts raised by Mr. Tripathi. We will be discussing in our next class, or maybe I will give you the answers in a manner that you can understand by yourself. There is no need to spend time together. Rather, we will start chemical bonding next time, which is a very huge chapter. Then we shall take a break. Yes, then we shall take a break for stoichiometry. Now, let me show you the melting point, boiling points, and densities. These are the things which we have to do. You know that melting point is the temperature at which a solid is converted to liquid. The phase changes from solid state to liquid state, temperature remaining constant by absorbing the latent heat of fusion, as you say. And in thermodynamics, we will say molar heat of fusion. Temperature doesn't change. And freezing is opposite. When a liquid is converted to the corresponding solid, that point is called the freezing point. Freezing point of a liquid is same as the melting point of the corresponding solid. Boiling point is the temperature at which a liquid state is converted to vapor state. At a constant pressure, say 1 atmosphere. If you change the pressure, then the boiling point will be more or be less. More the external pressure, the boiling point will become more. Therefore, cooking in cooker, in pressure cooker, we have high boiling point because the pressure develops much more because of that valve doesn't open unless a particular optimum pressure is thrust is given to that valve. So high pressure brings about the boiling point of that solution, liquid water and rice and all that liquid water which will boil the rice becomes 120, 130. So cooking becomes easier. And above a mountain, the pressure is low. So it boils, water can boil at 40 degrees, 70 degree, 80 degree, depending on the low pressure. And therefore it's difficult to cook on a higher altitude. So the boiling point of any substance is greater than melting point. We are talking about elements. We are talking about elements, not compounds. Now, metals definitely have a higher melting point, boiling point than non-metals. Non-metals are usually gases or liquids. Very few are liquids like bromine. Others are gases. And some of them are soft, low melting solids like phosphorus. Like the hero among them is sulfur, iodine. They are non-metals, but they are solids, but low melting solids. Because, in non-metals, the entities, the particles are in the molecular form, and there is a weak van der Waals forces between them, or at the most dipole-dipole attraction, which is not a true chemical bond. And therefore, when we melt such a substance which are covalent in nature, we do not break the covalent bond. When we melt, say, iodine, we do not break down I bond. We only weaken the van der Waals forces between I2. Therefore, the melting point is less. Why the melting point of iodine is greater and it is a solid at room temperature, bromine is a liquid? Because of their sizes. More is the size, we shall know in our chemical bond program that more is the van der Waals forces. Therefore, as you go down the group, the melting point, boiling point increases, particularly in halogens and noble gases. It increases because of the increase in size, increase in van der Waals forces. So, you see, few non-metals like carbon, one of the allotropes, diamond, has the highest melting point because we will study in carbon family that in diamond, it is a network structure. It is a single molecule with infinite molecular mass. Each carbon is bonded to 4 other carbon atoms covalently. Covalently bonded with 4 other carbon atoms, and as a result, it's an infinite network. So to break down infinite number of bonds in a diamond crystal is a stupendous task. And therefore its melting point. Melting point comes first, around 3500, which is the highest among elements. I'm not talking about compounds. There are many transition metal compounds which have still greater melting point than diamond, but I'm talking of elements. Now, the difference between melting point and boiling point is very large in metals. In metals, try to remember, everything is there in this note. You just write down at home, everything. The difference between melting point, first, if it is a solid, then first melting point will come at a lower temperature. Then you have to increase the temperature. Its temperature will rise. And when the boiling point will come, then it will vaporize to its vapor state. So the difference is large for metals. Why? Because during melting of a metal, you only weaken the metallic bond. About metallic bond, we shall study in our chemical bond program. But when we vaporize a liquid metal to vapor, you completely destroy the metallic bond. The atoms, they remain in the atomic state, isolated state, in which at which we measure the ionization enthalpy and electron affinity. That two definitions are hold good in isolated atoms. Even a metal becomes free, individual atoms are formed in the gaseous state. No metallic bond, no bonding between them, no association, no network formation, nothing. So that is why the difference is large. But in case of non-metals like chlorine, hydrogen, nitrogen, which are gases, you have to go in a reverse way. You have to cool down at some minus, say, minus 150 degree or minus 186. It will liquefy. It will liquefy. Nitrogen liquid will be formed at its boiling point. So the boiling point should be called a condensation point, the opposite you are doing. And then further you have to cool down, say minus 196, to make it frozen into, that is the freezing point, into solid, nitrogen solid. Now, if you start from nitrogen solid at minus 196, just I am, giving a fake value, I don't remember. Say minus 196, it is in the solid state, then you say minus 200, it is in the solid state, and you slowly increase the temperature, and it at minus 196 it will melt, and then it will become liquid, and slowly you increase the temperature at only minus 186, where difference is very, very small. Why the difference between melting point and boiling point, or in the opposite direction, the condensation point and the freezing point, the difference is small for non-metals? Because while you melt a solid non-metal like solid chlorine, solid hydrogen, whatever, you weaken the van der Waals forces. The van der Waals forces is maximum in the solid state. You don't, in any case, you don't destroy the covalent bond. So when you vaporize a liquid at its boiling point, you further weaken the van der Waals forces. So even in the gaseous state, there is van der Waals forces. There is van der Waals forces. Even although it is very, very less, but it is there in the gaseous state. That is why, since you are just weakening the van der Waals forces, you are not breaking a covalent bond. Therefore, the difference between MP and BP is very, very small. So with this introduction, let me show you first the data. Now look, the upper one is the melting point. The lower one, red one, is the melting point, and the upper one is, which is greater. Oh no, the lower one, say 181, lithium. Forget about hydrogen, which is H2. Its always melting point is lower than the boiling point. Minus 259 is lower than minus 253. Now see the trend of alkali metals. 181, alkali metals are low melting solids. 181 is the highest, and as you go down the group, 98 is sodium, 64, 39. So rubidium is very close to the body temperature. Sometimes it is, if you are a little feverish, then rubidium metal can melt on your palm top. But you have to hold a glove. You have to wear a glove to hold rubidium. Is a very reactive metal. Cesium is in fact becomes liquid at in our condition, as you know. In summertime, the temperature often remains more than 30. So cesium remains as a liquid state. Of course, inside kerosene, it doesn't mix with kerosene in the liquid state. Of course, inside kerosene, it doesn't get that temperature. That temperature kerosene will have an insulation property. Glass is there, so it remains as a solid. But when you open it, hold it using a glove in your hand and hold it, it will melt immediately, just like looking like mercury. And francium is 27, is radioactive, still less. So it goes on decreasing down the group. And so also their boiling point. See the large difference between a particular element's melting point and boiling point. 181 is 1347. Same is the case with every metal. The reason I have told you. And the alkaline earth metals are much greater than alkali metals. These are, 181 is the maximum. But in alkaline earth metals, it goes to 1278 because their metallic bond is stronger. We shall study about metallic bond. Then I will tell you what happens. This has a lower metallic bond, and down the group, as the size increases, metallic bond strength decreases. So the melting point also decreases. But in group 2, it is anomalous. There is no specific trend. 1278, then 649, a sudden drop, and then 839, again increase, and again decrease. So up to, no, yes, again increase, again decrease, and then 7 to 26. So 1278, excepting magnesium, if you just forget about magnesium, it goes on increasing. No. It decreases and then increases. Then increases. Decreases, increases, and then decreases, then increases. So there is no anomaly, but the most important thing is that they are higher melting than alkali metals because their metallic bond is stronger. They have 2 valence electrons. Now see, the transition metals, they have much higher melting point than other S block and P block elements. Now the highest melting, of course, diamond, forget about diamond. In a group, you find the melting point goes on increasing. Same is the trend with boiling point, increasing. You see any group, it goes on increasing. 1541, 1500, that is the only good group where it decreases, like other groups, because there is no such relativistic contraction effect or the lanthanide or D block contraction effect. So, but you see, titanium 660, 1852, 2027. So only scandium group there is a decrease because the F block contraction effect comes here. But in all other groups, there is an increase. No, there is a decrease. There is a decrease and then increases. 16. Oh, no. There is increase. Always there is an increase. Increase. I'm so sorry. So in all the groups, you will find there is an increase, excepting copper and zinc group. You will find scandium group, there is a decrease. See the black one, 1541, 1522, 921. All other groups, it goes on increasing. You will find zinc group, it is decreasing. Mercury is a liquid metal, minus 39 it is melting point. But see the difference between melting point and boiling point. That is why it is a metal. It decreases. And in copper group, copper is the highest, then gold, then the lowest is silver. 1083, 1065, then this is 982. The actual cause of this cannot be explained in any physical manner. We have to go to the quantum mechanics to explain that. So, but alkali metals can be explained. Alkaline metals, the anomalies, the irregular trend cannot be explained simply by saying something. Physical interpretation is missing out in general. But yes, quantum mechanics, they have proved. And if you look to the non-metals, the difference is very small. Minus 218, minus 183. Say nitrogen minus 210, I was selling minus 196. Minus 210, minus 196. The difference is not much, 15 or 14. The reason I have told you. And in boron family, it decreases up to gallium. Gallium is a liquid metal in our condition, 30 degree. It melts on the palm. You can use your palm, naked palm. It's not that dangerous like cesium. So you will find it will be melting on your palm top. So, but the difference you see, because the gallium remains as a diatomic molecule, Ga2. and there is van der Waals forces between them, and that is why van der Waals force is not much. So it is a liquid. It goes on decreasing and then increases. In carbon family, the hero is diamond 3547, and then it decreases, decreases, decreases. But lead is greater than tin. Similarly, nitrogen family, these are gases with a minus negative melting point, and it goes on increasing. Arsenic, why star mark? Because it at room temperature, if you heat, then it will, it will vaporize before its melting point. But if you want to see its liquid state, then you have to go for high temperature, high pressure. I'm sorry. I think, as far as I remember, need 7 atmosphere or something. Let me check my memory at what these things are written. Yeah. Arsenic is peculiar metalloid whose metal melting point looks greater than the boiling point. Ha ha ha. Actually, in 1 atmosphere, it vaporizes directly. It is volatile. 616 boiling point. And oh no, my memory failed. 28 atmosphere. If you want to see liquid state of arsenic, then the external pressure, air pressure, external pressure should be increased to 28. Then at that pressure, as you know, as you increase the pressure, the melting point will increase. So it is 817. Had it really melted at 1 atmosphere and shown its beautiful liquid appearance, then it would have been definitely less than 616. But since we are applying high pressure, that is why in the table it looks weird. The melting point is more than boiling point. I've explained everything. And this antimony, it goes on, increasing down the group as the metallic character increases. Again, bismuth is less than antimony. In oxygen family, also it is a gas, minus 218, then increase, 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 increase. So the oxygen family and halogens, they are cool. They are cool. No. Polonium is less than tellurium. Bismuth is less than antimony. But in halogen family and noble gases, cool. It goes on increasing. Minus 220 fluorine, minus 101, minus 7 because it's a liquid, and 1 plus 114 it is a solid. And astatine is almost an extinct element now, but someday before they have met the condensed state and studied the melting point is still greater than iodine. So also the noble gases minus 272, very close to the absolute zero. That is 0 Kelvin is minus 273.15. It is very close to that. That is about 1.15 like that. So then minus 249, it goes on increasing. Minus 189, minus 156, minus 112, minus 71. And in a period, it goes on increasing up to certain element and then decreases. As the metallic character increases, the metallic bond strength increases, more and more number of electrons participate. Even if it is the n-1d, metallic bond becomes stronger, it goes on increasing. You can have a look to this potassium, calcium, scandium, it goes on increasing and up to chromium. And then, of course, there's an anomaly here, there's a dip here. We're talking about the dip in manganese and then increases. I'll show you the transition elements in the form of a graph which I have borrowed from NCERT book. It's a very good. This is because it goes on increasing down the group. So titanium is less than zirconium, less than hafnium. Excepting the scandium group, which has not been shown, their trend is different. Scandium greater than yttrium greater than lanthanum. That is why they are not shown. Starting from titanium, you find the corresponding vanadium is greater than less than niobium, less than tantalum. But in a particular series, it goes highest up to group 6, chromium, molybdenum, tungsten. And then In the first series and second series, there is a dip at manganese and technetium, but there is no such dip at rhenium. A dip means the next element goes above it, but osmium doesn't go above rhenium. It falls down after tungsten. After group 6, it falls down, but rhenium is greater than osmium, then iridium, then platinum. Then there is a difference here. Copper, then copper, of course. But if you compare the groups, in a group, copper is the highest, the red one, then gold, then the lowest is silver. This is comparing the three elements in the group 11. So this is, the two dips you find in a transition series 1 and transition series 2. You must draw this diagram, and I have explained everything. And zinc group is the anomalous group, zinc, because they are not true transition elements. Their s electron does not participate in bonding. So it goes on decreasing down the group as size increases, and mercury becomes a liquid. The metallic bond strength is minimum. So these things yes, I have just written some words from metallic bond, which we will study in our chemical bond program. But this is very important. This is very important for your examination, particularly the competitive examination. Goes on increasing up to group 6. And then in first series and second series, you will find a dip in manganese. So that the next element, iron and ruthenium, they are higher than, and then in first transition series, the decrease is very slow. And then at nickel, there is a sudden dip to copper. Similarly, ruthenium is greater than technetium, and then is a sudden dip, and it goes on dipping down. So also there is no such dip in rhenium. From tungsten downwards, tungsten onwards, you'll find there is a sudden drastic decrease in melting point. You can have a look here in that series. This tungsten is the highest melting transition metal is tungsten, 3407. And then it goes on decreasing, and mercury is suddenly minus 39. Find there is always a decrease. So also it goes on increasing up to molybdenum 2617, and there is a dip suddenly 2172, and then ruthenium is greater than technetium, and then there is a decrease up to cadmium. Similarly, scandium, and it goes on increasing up to chromium 1857. Vanadium looks greater. Vanadium in this particular table, vanadium looks greater chromium. But how come I have given a data vanadium is greater than chromium? So this sounds, let me ask. Vanadium is 1910, chromium is little less. It melts. So in my table, I have not given 1900. This is something different. I have given more. Therefore, this data is not correct. Vanadium is little more than chromium. So we cannot write it goes on increasing. Vanadium shows in my table, and of course in the other table which I have borrowed from elsewhere, here vanadium is 1890 and chromium is 1857. In all cases, vanadium is greater. So we cannot say it goes on increasing up to chromium. So here I will make a change here in this particular graph. I will make it anomalous here, making vanadium here. Little greater than chromium. Titanium, then after that what? Scandium, titanium, তারপর তো vanadium, vanadium, chromium, manganese, ତଳକୁ ଖସିଲା iron, cobalt, nickel, ଏଇଟା ଏ palladiumଟା ଉପରର copper, zinc is not shown because their trend is completely different. So the scandium group is not shown, zinc group is not shown, and here we found an anomaly. Vanadium is slightly greater than chromium. Any question, Mr. Tripathi? See
No,
to
sir.
what extent we are analyzing. Our analytical level is, see, we are finding fault with the graph present in the NCERT book. Yes, Mr. Tripathi? Anything?
No, sir.
So in the second series, it goes on increasing up to niobium 24, and then there is a dip at molybdenum, and then it's interesting. If there is a not the deep at technetium, I'm so sorry. It goes on increasing up to molybdenum, chromium group. I'm so sorry, 26, and there is a deep at technetium, 2172, and then there is increase. Ruthenium is 23rd, and then there is a decrease. That's okay, but we don't accept this vanadium and chromium. Vanadium is more than, but here niobium is less than molybdenum, but vanadium is more than chromium. Distinctly in all data, in my data, ସେଥିରେ ତ ବାହାରିଲା 1910 ବାହାରିଲା, ଏଠି 1905. So ଆମେ ଏ ଡାଟାରେ ମଧ୍ୟ ଏଠି ମଧ୍ୟ ଆମେ ପାଇଲେ. So in whatever data we have seen, it says ଦେଖିଲେ 1890 and this is 1857 is chromium. So and ଆମେ ଏଇଟା ମଧ୍ୟ ଦେଖିଲେ. And if you look to images, ଏଠି এটা ଗୋଟେ କୋଉ source ରୁ ଆସିଛି, I don't know the same source or different source. Lanthanum is a different source. So lanthanum, body, if you look to the scandium, it goes on decreasing. Scandium, then yttrium, ठीक है तळକୁ এটা ହେଲା second, এটা ହେଲା first. So scandium ଟା ଟିକେ ଉପରେ ଅଛି, ଦେନ୍ ଇଟ୍ରିୟମ୍ ପାଖାପାଖି ସମାନ ବୋଲି ସେ କହୁଛି, ଦେନ୍ ଲାନ୍ଥନମ୍ ଇଜ୍ ଲେସ୍. କିନ୍ତୁ ଆମ ଟେବୁଲରେ ଯେଉଁ ଦେଇଛି ଡେଟା, ସବୁ ଟେବୁଲରେ ସ୍କାଣ୍ଡିୟମ୍ ଅଧିକା ଦେଇଛି. ସ୍କାଣ୍ଡିୟମ୍ ଇଜ୍ 1539 ପାଖାପାଖି, କିନ୍ତୁ କମ୍ ଏ ଟେବୁଲରେ ଗଲା, କିନ୍ତୁ ଏଇଟା ଠିକ୍ ଦେଇଛି. କିନ୍ତୁ ହ୍ୱାଟ୍ ଆବାଉଟ୍, ହଁ ଏଇଟା ଦିସ୍ ଡେଟା ଆଇ ଥିଙ୍କ ଆଇ ୱିଲ୍ ରିପ୍ଲେସ୍ ଦିସ୍. ଦିସ୍ ଡେଟା ଇଜ୍ ଭେରି ଗୁଡ୍. ଏ ଦେଖ ଟିକେ ଅଧିକା ଦେଇଛି ଭ୍ୟାନାଡିୟମ, ଟିକେ ଅଧିକା ଦେଖ, ଟିକେ ଅଧିକା ଦେଇଛି, ହଁ କି ନାହିଁ?
Yes, sir.
So I will snip this one and replace that one. In my original data, I mean file, let me not dishonor the NCERT, let it be there, but let me give a less importance to that, because it misses the actual thing, it is wrong. So that is why, what do you think? Should I eliminate it totally or keep it just for reference, telling the students that in your book this is given, but actually it should be this. हाँ कि नहीं? अरे हाँ कि नहीं मो?
Yes, sir.
Again, sir.
Well, lanthanides and actinides, they have lower melting point than transition metals, and in a series there is no fixed order. Then coming to density, this is all about, we have discussed in alkali metals, there is a very good trend. In alkaline earth metals, there is no particular trend, but it is greater. Transition metals are in general much greater. Scandium group रे कम, तथापि the lowest melting transition metal, the lowest melting transition metal क्या होगा कहला? I think it is here. Of course, एमाने जो the true transition metals नुहंती, even scandium is not a true transition metal. But in the D block, the lowest is mercury. Being a metal, it is a liquid. So the lowest melting metal in D block is mercury. Understand? The highest melting transition metal is tungsten. Because in the group it goes on increasing. In a series it goes on touching, as per the graph that we have seen, goes highest value, then decreases. But only in the first series and second series there is a dip at manganese and a dip at technetium, and then it increases, then decreases. Right? Got it?
Sir,
Huh.
sir, କଣ କହିଲେ ଆର୍ସେନିକ ରେ ମେଲ୍ଟିଂ ଟା ଅଧିକ ବଏଲିଂ ଠୁ
Huh?
ଆର୍ସେନିକ ରେ ମେଲ୍ଟିଂ ଟା ବଏଲିଂ ଠୁ ଅଧିକ
କାହିଁକି? ସ୍ୱୟଂ କାହିଁକି?
सर सर जो मेल्टिंग टा होची सर 28 एटमॉस्फेयर रे होची सर ସେଥିପାଇଁ
Yes,
ଅଧିକ
yes. ବିସ୍ମୟ ମଧ୍ୟ ଜାଣିଛି। ମତେ ତ ଲାଗୁଛି ବିସ୍ମୟ and ସ୍ୱୟଂ ତାଙ୍କର analytical level almost same. ତାଙ୍କର power of analysis, grasping level and ଏ ସବୁ ପାଖାପାଖି ସମାନ। ୟେସ୍, ତମେ ଜାଣିଛ ଯେ 1 atmosphere ହଁ
ହିଲିୟମ ରେ କାହିଁ ସେମିତି ହଉଛି?
କଣ କହିଲ?
ହିଲିୟମ ରେ ବି ସେମିତି କାହିଁକି ହଉଛି?
ଓ କାହିଁକି ଭୋଲାଟାଇଲ୍ ହଉଛି? ବିକଜ ତାର ବଣ୍ଡିଂ, ତା ଭିତରେ ଯୋଉ ଷ୍ଟ୍ରକ୍ଚର ଅଛି, ଇଟ୍ ଇଜ ଇଟ୍ ଇଜ ଏ ମେଟାଲଏଡ୍, ଆର୍ସେନିକ ମେଟାଲଏଡ୍ ରେ ଆସୁଛି। ଦେଖ ଏମିତି 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 ବେଳକୁ ଆର୍ସେନିକ ଇଜ ଏ ମେଟାଲଏଡ୍। ତେଣୁ ତା ଦେହରେ ନନ୍ ମେଟାଲିକ୍ କ୍ୟାରେକ୍ଟର ଅଛି, କୋଭାଲେଣ୍ଟ ବଣ୍ଡିଂ କ୍ୟାରେକ୍ଟର ଅଛି, ଆଣ୍ଡ ମେଟାଲିକ୍ ବଣ୍ଡିଂ କ୍ୟାରେକ୍ଟର ବି ଅଛି। ତ ଯୋଉ କୋଭାଲେଣ୍ଟ ବଣ୍ଡିଂ କ୍ୟାରେକ୍ଟର ଅଛି, ସେଥିରେ ତାଙ୍କ ଭିତରେ ଯୋଉ ଆସୋସିଏସନ ନେଟୱାର୍କଟା ବହୁତ ୱିକ୍। ସୋ ମଚ୍ ସୋ ଦ୍ୟାଟ୍ ତାକୁ ହିଟ୍ କଲା ବେଳକୁ ତାର ମେଲ୍ଟିଂ ପଏଣ୍ଟ ଯେତିକି ହବା କଥା 1 atmosphere ଆସିଲା ବେଳକୁ ସେ ଆଉଟ୍। ଯେମିତି ଆୟୋଡିନଟା ଏକ୍ଜାକ୍ଟଲି ସେଇଭଳି। ଆୟୋଡିନ ତାଙ୍କର ଭ୍ୟାଣ୍ଡରୱାଲ୍ସ ଫୋର୍ସେସ୍ ଯଦିଓ ଷ୍ଟ୍ରଙ୍ଗ ସଲିଡଟା, କିନ୍ତୁ ମେଲ୍ଟିଂ ପଏଣ୍ଟରେ ରିଚ୍ କଲା ବେଳକୁ ଯୋଉ ଟେମ୍ପରେଚର 100 କେତେ ଦେଖୁଛ, ସିଏ 114, କିନ୍ତୁ ତା ପୂର୍ବରୁ ସିଏ ଭୋଲାଟାଇଲ୍ ହେଇଯାଇଥିବ। ମେଲ୍ଟ କରିବ, ତାର ମୋଲ୍ଟେନ୍ ଷ୍ଟେଟ୍ଟା ଆମେ ଦେଖିପାରୁଛେ ଆୟୋଡିନର ବୋଲି ଲେଖା ହେଇଛି, କିନ୍ତୁ ଆର୍ସେନିକର ମୋଲ୍ଟେନ୍ ଷ୍ଟେଟ୍ଟା 1 atmosphere ଦେଖାଯିବ ନାହିଁ। 616 ତା ପୂର୍ବରୁ ସିଏ ଭୋଲାଟାଇଲ୍, ସେ ଭେପର ହେଇଯିବ। କାହିଁକି ନା ତା ଭିତରେ ଇଣ୍ଟରମଲିକୁଲାର ଫୋର୍ସେସ୍ ଆର୍ ୱିକ୍ ମେଟାଲଏଡ୍ ସକାଶେ, ଏବଂ ସେ ଉଡ଼ି ପଳେଇବ। ଯଦି ତୁମେ ଚାହୁଁଛ ତାକୁ ମେଲ୍ଟିଂ ଷ୍ଟେଜରେ ଦେଖିବା ପାଇଁ, ତେବେ ତୁମେ ତାକୁ 28 atmosphere ଦେଲେ କ୍ଲିୟରଲି ଲିକ୍ୱିଡ ଦେଖିବ। କ୍ଲିୟର ହେ? ଏସବୁ ଡିପେଣ୍ଡ କରୁଛି ଇଣ୍ଟରନାଲ ଷ୍ଟ୍ରକ୍ଚର ଉପରେ, which is very complicated,
Yes, sir.
varies from element to element. So I think we close today's session. Okay. I'm a temple person now. Although I have told you, I have shared, majority of Hindus, they love to go to temple as a matter of routine. They should, I don't deny, but I am not a temple person. I find my temple inside myself. Try to find. So, not to, the religion or your faith is personal. To me, a religion, faith is absolutely personal. And when we go to a temple, amongst others, yes, if it is a mass prayer, usually when we congregate together, we are distracted. our level of concentration becomes less. This is the reality. But as a matter of routine, we beg for something for our children, almost like begging to God, as if God is non-existent here, there, and inside a person, inside any living being. Like, yeah. So we feel that the power is concentrated in a temple. There are thousands and thousands of temple, and temple has become a center of business nowadays. So, despite I tell this, but I have been given the, I don't say opportunity, the responsibility to manage the temple. So, as a manager of the temple, I'll be visiting. Of course, when I visit, I do not have any, negative feeling for any deity. Although I am not a very strong, ardent, practitioner of deity worshipping, but I have all my reverence, because I also respect the people's faith. I respect that, and I find there also power. Everywhere there is power. We miss out the presence of power when we are outside, or we are talking with someone, we are outrageous with someone, we are angry with someone, we are mad at someone. We forget that we are amidst the same source of power. So I close to now. We'll finish. I think we could not finish today. No, we will finish on, definitely on. Maybe we will change the timing. I will tell you after August 15th. August 15th is nearing. It will be 4:30 to 5:45, or 4:15 to, if you start at 4:15, it will be better. 5:30, 5:45 would be better. Bye bye. ତମ question ଟା answer କରିକି ମୁଁ ଦେବି. Of course, all my these things, out of the way, things are being recorded, but I don't mind. Whoever will come to the end of my video, he will just know my viewpoint. This is my viewpoint. I will never ever want that your viewpoint will be same as my viewpoint. Bye bye.
Thank you, sir.
Thank you, sir.